Here is a simple puzzle for you. You are playing a game with some colored boxes. In each round, you identify all the boxes that differ in color from its left neighbor. And then you delete all these identified boxes simultaneously. Your goal is to find out after how many rounds will all the boxes disappear. For example, if this is the initial configuration, then in round 1 you mark all the identified boxes with a star and then you delete them simultaneously and concatenate the remaining section to get this configuration. Then you repeat this process again in round 2, marking these boxes with a star and deleting them all at once. In round 3, you can notice that only a single R can be deleted for the rest of the 3 rounds. So you can say that this configuration would require 5 different rounds for all the boxes to be deleted. Now, writing a brute force approach to simulate this process is pretty simple. However, the time complexity of that approach would be O of n square. But can we do better? Can we improve it to O of n using some algorithm and data structures that we already know? We will find out in this video. The name of this problem is Cosmic Rays and it appeared in Codeforces Epic Round August edition of 2024. Although this is a 2200 rated problem, you will see that the final solution is pretty elegant. It can be implemented in just 15 lines of code. This is the problem description. Take a minute to pause this video and think about how you would devise an O of n algorithm for this problem. Before we discuss the solution, let us look at an alternate representation of the initial configuration. Instead of having 3 copies of the same color, we can compress it into one single colored box and label it as R3, representing that there were 3 copies of red box at this location. We repeat this for all the colors that follow to get this configuration. You can clearly see that there is a bijection between these two configurations. Therefore, we do not lose any information about the problem. Plus, this configuration allows me to display more data on your screen. This compression technique is known as run length encoding. But now that we have compressed these boxes into one single box, instead of calling this as a box, I will start calling this compressed version as a block. So this is a block of 3 red boxes. This is a block of 2 green boxes. This is a block of 2 blue boxes. If we have 3 blocks, then there must exist some strategy using which you can collapse these blocks. Now, what happens when you append an additional block B2 at the end? Will the strategy of collapsing these 3 blocks change? No, it won't change because the incoming block B2 will only be affected by the elements to its left. It can never affect the elements to its left. Therefore, we can conclude that in this problem, a suffix can never influence a prefix. And where have we seen this pattern before? We have seen this pattern of suffix never influencing a prefix in standard prefix DP problems. For example, if you recall the subset sum problem, we define DP of x to be true if it is possible to create a sum x using the ith prefix. Then we ask ourselves what happens to this DP array after you append a new element to the ith prefix. That is, how do you refresh the DP values when the prefix moves from I to I plus 1. So we can think of applying the same technique over here. However, I should mention that at this point of time, this is just a hunch. Prefix DP approach might work, it might not work for this problem. But we should at least explore that train of thoughts and see where it leads us. But to do that, we need to figure out what do we want to track in our DP so that we will be able to refresh the DP values. The thing to track in subset sum DP was pretty simple. You could just track whether a subset sum is possible, and then refreshing it was pretty simple. But it is not that simple in this problem, and we need to be a bit creative with what exactly do we want to track in our prefix DP. Let us start with the simplest guess. For each prefix, we will track the number of rounds needed to collapse that prefix. But is this information enough to refresh the DP values? That is, if I append a new block at the end with value B20 indicating that there are 20 blue boxes at the end, can you tell me the new number of rounds that are needed for this bigger prefix? You cannot confidently say that the number of rounds would remain 20. It can be more than 20 as well, depending upon whether this last element is a blue box or not. Therefore, it is clear that tracking just the number of rounds in our DP is not good enough. However, we did get a hint on what should we track instead. For each prefix, let us now track the number of rounds as well as the last block of that prefix. Given this information, can you refresh the DP values? That is, can you tell me the updated value of both these parameters when you append a new element at the end? Is it an easy task? In some cases, yes, but in most of the cases, the answer is no. Why? Because if the last block of the prefix is G5 and you append 3 copies of a blue box, then you can confidently say that all these 3 copies of the blue box would participate in previous 3 rounds that G5 participated in. Therefore, the total number of rounds for this prefix and this prefix does not change. However, if the last block was G3 and you appended B5, the only thing that you can confidently say is that 3 copies of this blue box would participate with G3. But what about the remaining 2 copies, B2? Can you confidently say that B2 will participate with whatever element is present over here after round 3? No. You need some more information for the element that is available over here after round 3. Therefore, tracking this number of rounds and the last block is also not enough for our DP, but we did get a hint of what we need to track. In our DP, for each prefix, let us now track the number of rounds as well as all the previous blocks of that prefix. Using this information, can you refresh the DP values? But before you do that, you might be wondering, how is it possible to track so many different values for each of the prefix? Even bit masks can only track a limited set of elements. Won't you get memory limit exceeded if you track so many elements for each prefix? But you don't need to worry about that right now, because later in the video, using some interesting properties of this problem, I will show you a technique using which you don't have to worry about the memory limit being exceeded. But for now, let us focus on the correctness of the algorithm if we were to track these quantities. If you append a new block B5 at the end, you can see that 3 copies of B5 will participate with 3 copies of G3, and then the remaining 2 copies of B2 will participate with R2 because red and blue are different. Therefore, if you track the entire blocks of the prefix, you will be able to find out the total number of rounds as well as the new set of blocks. It looks pretty simple and innocent, but the reasoning that I've just shown you is incorrect. It has a major flaw, and I want you to pause this video right now and think about the flaw in the reasoning. In our previous reasoning, we forgot about the fact that while B3 and G3 were participating together in 3 rounds, in those 3 rounds, R2 was also participating with its left neighbor. And by the time we had B2 over here, R2 has vanished. Therefore, this information is of no use to us. So, we can say that even tracking the entire block of the prefix is not enough to refresh the DP values. So we need to be a bit more creative on what do we want to track instead. Our last approach did not work because we did not care about the block that is currently located at this position. Instead, we wanted to know the block that would appear at this position after G3 was eliminated from the game. But if someone gave you that information, you can easily find out the number of rounds needed for the I plus 1th prefix. So now let us model this as a graph problem. We will say that there is an edge from G4 to B5 indicating that after G4 is eliminated from the game, B5 would appear as the terminal element in its location. This doesn't mean that B5 was to the left of G4 in the original configuration. No, this just means that once G4 gets eliminated, B5 would appear over here. Suppose for the ith prefix, you had this graph given to you. Now, using this graph, can you refresh the DP values? That is, if you append a new element, suppose it is B20, can you find out the number of rounds that are needed to delete this newly appended element? Since you have this graph, you can actually simulate the entire process. So we have 20 copies of the blue box. Since the terminal element is red box, 2 copies of it would participate with R2, and then R2 would get eliminated and we would have B18 remaining over here. But what happens after R2 gets eliminated? By definition of edges in this graph, we know that after R2 is eliminated, B2 would appear. But what happens when B2 is present over here and B18 is present over here? So you can clearly see that this block can no longer participate as long as this block is present in this graph. Therefore, it will inflict a waiting time of 2 minutes for this block before it starts its own elimination process over here. But after 2 minutes have elapsed, this block would vanish, and then the new block that would appear in its position is P3. Now for this P3, 3 copies of it can participate with B18, which was waiting for B2 to go away, and then the frequency would become B15, and then P3 would get eliminated. And by definition, after P3 is eliminated, G4 appears. So 4 copies of this blue box will participate with 4 copies of this green box, and you get B11. But after B11, we know that once this is eliminated, B5 would appear. Therefore, B11 would be on hold because the terminal element is B5. So B11 cannot do anything for the next 5 rounds, and that is why we add a waiting queue of 5 for this same colored box. But once this gets eliminated, W3 would appear, and then W3 and B11 can match to create B8. And once W3 vanishes, we have B8 on the right hand side and T30 on the left hand side. So 8 copies of this node will participate with 8 copies of this node to bring the frequency to 0. Therefore, you can now see that the number of rounds that are needed to clear this block is not exactly 20. It is something more than that. And what is that quantity? It is equal to the number of identical colored boxes that you encountered on the journey, because the identical colored boxes will induce a waiting time of this frequency. Therefore, the answer for this block is the frequency of this block plus the sum of same colored blocks encountered on the path. So now you can see that in hindsight, we should not have tracked the number of rounds or the last block or the entire block of the prefix. Instead, we should track the number of rounds in which this block will be active. That is, how many rounds are needed to clear out this 20 blue boxes. That is one information that we should track. And the second information that we should track is this graph. That is what happens to a node after it is eliminated. That is, what is the new terminal node that would appear at this position. Now, so far we have just assumed that someone gave you this graph. But how do we actually construct this graph so that we can implement the DP solution? But here's the interesting part. You actually do not need to worry about any algorithm to create this complicated graph. As long as you can refresh this graph after appending a new element to the prefix, you should be fine. And in the previous slide, we have already seen that to refresh the graph, we need two things. One is the number of rounds for which the terminal element would be active, and that we have already determined to be the frequency of this element plus the blue nodes that we encounter on the journey. And the second thing that we need for refreshing this graph is the location of the node that would replace the terminal node after it has been eliminated from the game. And we have already seen that we were traversing to the left as far as possible, and then after all the copies of this blue node were eliminated, 15 copies of T15 remained. Therefore, we can simply add a curved edge from this node to this node, and we can update the label to 27. Why 27? Why not 20? Because these labels represents how many rounds will this blue node act as the terminal node. And we saw that it will at least act as the terminal node for 20 rounds, but then there was a waiting period of 2 plus 5, that is, it will start acting as the terminal node for 27 rounds. Another way to look at it is, once R2 was eliminated, B2 and B18 was present, but since they were of same color, we could have just combined them into B20, and that is another way to arrive at this B27 number. Now, once you have written the algorithm to refresh the graph, you can see that the graph for the ith prefix would be created from scratch via induction. Now this might be pretty weird to some of you who are not familiar with Prefix DP. That is, how come such a complicated graph is being created automatically by just adding one single edge and maybe refreshing the label of one node? But that you can figure out if you solve more problems on Prefix DP and if you try to do a dry run of this DP on paper. To implement the ideas that we have discussed so far, we need a data structure that can add an edge from one vertex to the other vertex. It should be capable of modifying the labels of old vertices, and it should be able to traverse the graph by following the chain of edges that are present in the graph. And you must already be familiar with the adjacency list in C or C++ that can act as your graph. So there is no difference between this and a regular graph. But what would be the time complexity? So even though we are traversing a lot of elements to figure out the waiting time, notice that any element will only be traversed only once, because as soon as you traverse this, you will never create an edge like so. You will create a curved edge. Therefore, every element will be visited only once. So, just like DFS, the time complexity would be V plus E in the graph. Therefore, if you use the graph representation, you can solve this problem in O of n. All you have to do is create a graph to represent the chain of replacements, and then every time you append an element to the prefix, traverse the graph, figure out the waiting time, update the label, and add an edge from this to the element that would be replaced. However, this is not just a random graph. This graph has very interesting properties. The first property is that most of the edges that you see over here, they are line edges. So this is a directed line graph, and there are some curved edges as well. However, the property of curved edges is that every node that is below the curved edge, they are not relevant anymore, because there is no way to enter any of these edges because this link is broken. Therefore, we don't really need to explicitly create a graph to solve this problem because of the special properties of this graph. And the data structure that can replace a line graph with curved edges is called stack. But at this point, I should mention that even without learning the concept of a stack, you will still be able to solve this problem using the concept of graph and DFS, because even if this is a special type of graph, all the general graph algorithms such as DFS would still work on this graph. Let us talk more about why this graph is exactly equal to a stack. In this graph, notice that when you were making your journey from right to left, when you finished the journey, you were planning to add a curved edge from the start to end. And all the nodes below the curved edge are now irrelevant because there is no entry point for them. So you can actually delete these elements under the curved edge. This is exactly similar to what a stack does. A stack basically says that if you have a stack, if you want to traverse the elements from top to bottom, after you have seen the element, you actually need to delete this element to go to the next element. And that is exactly what we want, because if you want to go over here, we want to delete this element. So instead of creating this graph explicitly, we can create a stack instead. Now what is the connection between these edges and a stack? So in stack, you can say that if an element y is below x, then you can say that there is a curved edge from x to y. So in that regards also, this line graph with curved edges is exactly same as a stack. Therefore, if you want a fancy way of implementing this problem, you can solve it with stack. And in fact, for all the problems on stack that you would encounter in future, you can solve it with this line graph as well. And I would argue that having this graph representation is easy for some people to visualize how problems that deal with stacks work, because you might have heard of problems like next greater element, previous smaller element, or stock span. So these are standard problems that utilize the concept of monotonic stacks, and a lot of people struggle with how monotonic stacks really work behind the scene. But if you create this graph representation on paper, you will quickly be able to visualize the main principle behind these stack algorithm. That is, we need to create a lot of curved edges so that the elements below the curved edges are deleted, and the time complexity would be similar to DFS, which is O of V plus E. Some of you might find the algorithm that we have discussed so far pretty magical. Therefore, let me show you a dry run of how the algorithm works behind the scene using DP, induction, stack, DFS graphs, and all the things that we have discussed so far. We will build this graph for each prefix and we will see how the graph is refreshed. For the first prefix, we just have one node with frequency 4, so it will stay alive for 4 rounds. Then when you append G1, then one copy of this green node would participate with one copy of this blue node. And after this green node is eliminated, 3 copies of this blue node would remain. So that is why we add an edge from G1 to B3. What happens when you append B4? If you append B4, one copy of B4 would participate with one copy of G1. But after G1 gets eliminated from this graph, you can clearly see that B3 would remain. And since B3 would remain over here and B3 would also remain over here, therefore a waiting time of 3 would be induced for this node. So therefore the total waiting time is 4 plus 3, that is 7. So this is the graph that would be created. Now what happens when you append R4? So when you append R4, you know that this would be active for 7 rounds. Therefore 4 copies of it can participate with R4. Then we can clearly say that once R4 gets eliminated, only 3 copies of this node would remain. Because remember, the edges should point towards how many copies of the new color would remain after this color has been eliminated. Then what happens when we append B7? If you append B7, 4 copies of this node can participate with R4 and then 3 copies would remain. But if 3 copies are remaining and once R4 is eliminated, B3 emerges. So there would be a waiting time of 3. Therefore, this B7 will wait for 10 rounds for it to be cleared. And finally, what happens when you append G6? If you append G6, 6 copies of it can participate with 6 copies of this. Why? Because this will stay active for 10 rounds. So after 6 copies has participated, the remaining copies that would remain is B4. So that is why we create an edge from G6 to B4, and from B4 we know that it will not have any remaining element after B4 is eliminated. For the code, we will build the answer prefix by prefix. First of all, we need to figure out the frequency of the block that is added and its color. For example, B20. Now, we need to figure out how many rounds will it take to completely delete B20. We know that it has to be at least 20 rounds because only one copy of it can vanish in one round. But it can definitely be more than 20 depending upon whether the left neighbor is of same color or not. Then you start traversing the graph from right to left. And how do you traverse the graph? By looking into the stack, because stack is the graph. Then if you encounter an element with the same color, which you can identify with this condition, you know that the waiting time will be increased by the frequency of that color. So that is why you increase the waiting time. And then you need to use this edge to go to the next node. But how do you traverse an edge? To traverse an edge, you need to use the stack.pop function. This function is equivalent to traversing an edge in this line graph with curved edges. But what if you meet a node which is of different color? So if it is of different color, then you can participate with that node for as long as you can. So that is why you participate with that node as long as you can, and then you use this edge to go to the next node. And how do you traverse an edge? Using stack.pop. Finally, it is possible that when you are at a node and you participated with this node was not completely eliminated because this got eliminated. Therefore, if this node is not eliminated, you push it back on the stack, indicating that some copies of it are still remaining. Then you need to refresh this graph. How do you refresh this graph? You can simply refresh the label by saying that the label is the number of rounds that it was alive for, which we have already determined here. And this curved edge would represent the next node that would take over. And the next node is the one that we last encountered in the stack. So we don't really need to do anything. All these vertices already got deleted when you traverse this edge in the stack. So you just have to push this element to the stack and this curved edge will automatically be created. And what would the final answer be? That is, how many rounds will it take to finish the entire array? You can clearly see that it will be the maximum value of number of rounds for each node to be deleted. For example, if it takes 27 rounds for this node to be deleted, and if it takes 32 rounds for this node to be deleted, then the total number of rounds that will be played is 32 only. And you can see that the time complexity of this code is O of n because we are just performing a DFS on this graph. We are not traversing any element more than once because of this gap over here. And in stack terms, you can see that every element is pushed into the stack once and popped in from the stack once. Therefore, the time complexity can never be more than O of n. If you had to take away just one thing from this video, I want you to remember this statement that all stack problems are graph problems. That is, if in future you ever get confused by stack or monotonic stack problems, try to visualize it as DFS and graphs, and the proof of correctness will become apparent to you. As a practice problem, you can try out these famous interview questions, which is stock span and the next greater element or the previous smaller element. But if you want some non-trivial problems which utilizes the concept of stack as a directed line graph with curved edges, I will create a practice contest in my group, the link of which you can find in the comments below on YouTube. And there I will also add the link to my code, some similar videos that use the same intuition, and the slides that you have seen in this video. All the code that we have discussed in this video will also be available on cfstep.com.